And okay, let's now discuss um let's now continue the discussion we started last week. Um so we had manifolds, right? We defined smooth manifolds, okay? And we defined smooth maps. Okay? But one thing that was funny about this definition is that somehow in the definition of smooth maps, we never talk about the derivative of the map itself. Okay. We somehow defined the notion of differentiability of a map without ever talking about the derivative of the map. And I'm not saying we didn't use the definition of the derivative at all, because we did, right? If we remember, to define smooth map, so to call a map F from manifolds M and N is smooth if for any chart V, sorry, U, phi around. So for any point P and any chart U phi around P and V psi around F of P, the map with appropriate domain and range, um, psi compose F compose phi inverse is smooth. And recall that this map is now a map from a subset of Rn. So it's a subset of Rm into a subset of Rn. So we can talk about what it means for this map to be smooth because we define smoothness of that map. Yeah, but this is still a little weird because we're defining the smoothness of something in relation of how it you know in relation to the smoothness of another map, right? This um diagonalizability. Um, I mean, it's more like a change of basis, more than diagonalizability. Is because this is a coordinate representation. So this is a coordinate representation representation of it. Um, it's okay. We have this coordinate representation of F, and we talked about the smoothness of this map, but the main idea was to generalize all these things, right? So we should move away from coordinates for a little bit. We'll come back to coordinates as always because computations are much nicer in coordinates for the most part. Um, but yeah, so this definition sort of leads us to asking about what the derivative of this map actually is, right? So what is the, I'm going to put this in quotations, derivative of it. Yeah. Um, so okay, let's now pull back. Not pull back. Let's let's take a step back and let's see what the main things about the derivative are, right? So one, the derivative is a linear map, right? So the derivative um at P in M. So we fix a point P and then we talk about the derivative at this point and then we like generalize this. So the derivative must be a linear map. Okay? But this already poses an issue because manifolds don't necessarily come with any vector space structure, right? We saw how the sphere was a manifold, but a sphere is not manifestly linear in any way, right? So this is the first red flag, okay? So we have to somehow define vector spaces at each point or for each point there's a vector space that the derivative is allowed to act on. Yeah. So note M may not be linear, be a linear space. And so we need some vector space that I will just for foreshadowing call TPM. Okay, vector space TPM at the point P. So basically the idea that we will do is we'll take um we'll define a vector space at each point. Okay. And we'll see how somehow these vector spaces will all be pretty much the same, at least up to isomorphism. Okay, are there any questions for why we need a vector space at each point on M? Because this is a very abstract concept. It's a very confusing concept. So are there any questions on this?
Yeah, quickly. How would they be different if, how would they be different from each M?
Do you mean each P or each M? Sorry.
Sorry, each point. How would they be different from each point?
Okay, so I mean they might be different because okay, let's draw a picture. So let's say we had a circle, right? And now I want okay, so this is my point P. And now I ask myself, okay, intuitively speaking, what vectors, quote unquote, because on the circle itself, there are no vectors, right? Because the circle itself is not a sorry, it's not a vector space. So I have to somehow build a vector space based at the point P for my derivative to act, right? Um, and the most obvious one, when you think about it for a little bit, will be the vector space that sort of looks like that in this ambient space, right? I'll explain why this is the case in just a minute. But if you take this for granted, right? If you accept the fact that this should be a good vector space, um, I mean, one of the reasons it's a good vector space is because it's tangent, and the derivative is sort of a tangent because we look at the tangent line, right? Um, and this is tangent to the circle, and it's a good linear approximation for the circle in some small neighborhood around P. Okay, so that's one of the reasons why this is a good line. And then if we move to this other point over here, and we say, okay, we want to look at this tangent line, this vector space looks like this, right? So you see how this vector space and this vector space, even though they look the same, they're not actually the same vector spaces. So they're only the same up to isomorphism. Yeah. Does that make sense? Okay. Yeah, and this is why I call them TPM, because this will be the vector space that we want our derivative to act on will be the tangent space. So it'd be the tangent space at P. So tangent space of M at P. And one way to think about this is the best linear approximation to my function. Sorry, to my surface. And how would we define isomorphism in this regard quickly? I mean, in this case, we're looking at isomorphism of vector spaces. Um, we'll see in the case of um, we'll see in the case of Lie groups, which I'll introduce today. There's a canonical isomorphism between tangent spaces, but that's not necessarily true in an arbitrary manifold. Okay. So I've already sort of introduced how we would define such a tangent space, right? We want to look at a linear approximation of the surface at this point. One way to do this is if I'm a particle, right, on this surface, and I ask myself, if I move a little bit, I have some velocity vector, right? What is the best linear approximation for my next position in time? So if I take a little step forward in time, what is the best approximation to my position? And this is basically the derivative of my like trajectory, right? If I just take the derivative and I multiply it by the time step and then I add it to my current position, assuming we have some ambient space where we can do all of this, um, this is just taking the derivative um, of the curve, right, to get the velocity. Does that make sense on why we're looking at curves now? Like why we'll specify tangent vectors to be derivatives of curves? Because if I have some motion in this space, the best linear approximation for a small like step in time would be to like take the derivative and then do the usual linear approximation stuff. Okay. Um, okay, so let's let's actually look at the case of the circle a little bit and let's see if the ideas that we've come up with make sense. So we would really want that the velocity of the so now assume that the circle is sitting inside R2. Okay. So assume um S1 is sitting inside R2. Okay. Usually S1 is defined independently of any ambient space. In the case of manifolds, when we define a group structure on it, we'll see that it's much easier just to define it as a subset of the complex numbers. But yeah, so assume that the circle is sitting inside R2 and gamma is some curve, okay? Um, differentiable, of course. And we can talk about differentiability and we can talk about the derivative and stuff because this is a subset of R2. Okay. So if we wanted, we can look at gamma as a curve into R2. And now we can talk about the derivative of this map. And we'll identify the derivative of that map with the derivative of this map. Okay. This we would hope, we hope, um, we hope that gamma and gamma prime be tangent at each t in this, right? The reason we want it to be tangent is because we want this best linear approximation, and I'm saying that this best linear approximation is this line. And this line is the tangent line to this circle. Okay. So let's look at this very quickly. So we know that so I'll denote the inner product like this. Okay. So I'll denote the inner product like this. And what we want to show is we want to show that gamma prime gamma is equal to 0. How do we do this? Note that since gamma is on the circle, right, its inner product with itself is equal to 1, right? Because its length is 1. And now we can differentiate both sides with respect to t. Okay, so we have 0 because the derivative of a constant is 0. D by dt of gamma gamma. But if you write out the definition of the inner product in this case, you'll see that it's gamma 1 squared plus gamma 2 squared. And then if you think about it a little bit more, you'll see that this is nothing but 2 times gamma gamma prime. Okay. One way to see this is you can think of this as a product rule, and what you end up with is gamma gamma prime plus gamma prime gamma, but by the symmetry of the inner product. This is just 2 gamma gamma prime, which then gives us, right, that gamma and gamma prime are tangent at each point. So for each time, the derivative of gamma is tangent to gamma itself. Okay, so this is very good, right? So this sort of gives us motivation um, to look at tangent vectors not as vectors, but as the derivative of certain curves through our space. Are there any questions on any of the? I mean, in this case, the derivative is just the derivative in R2, because S1, we're looking at S1 as the subset of R2. On a manifold, what does this look like? We'll define that in just a minute. Okay. So now let's let's look deeper at um for rotating field. What do you mean rotating field? Perform this circle, call it phi inside of a rotating field, say B, and I want to find out the derivative in this sense. Uh, I formed a surface of a rotating field. Do you mean like a surface of revolution? I'm slightly confused. Um, yeah, so we'll define the derivative on a manifold in just a bit. Um, but I'm just making sure that in the case of like embedded submanifolds or like manifolds within manifolds, um, or manifolds of Rn, submanifolds of Rn, it makes sense why we look at like the derivative of curves um, to talk about tangent vectors. It's mainly this is our motivating definition. Okay. Um, we'll I'll hopefully make it more clear in just a moment. Um, so okay, let's now let's look at the derivative of curves in Rn slightly longer, and let's you know see what we can do with this. So one of the issues with this definition is one, it doesn't make sense in a general manifold because we come back to the same thing of like, okay, we don't have a metric or we don't have an inner product. So we don't really know what any of this means, right? All we know is that instead of looking at vectors, we have sort of reduced it to finding these tangent vectors um, that are basically derivatives, whatever that means, of curves of maps. So the derivative of curves on our manifold. Um, and to drive my point slightly further, let's stick with Rn for a bit, okay? And let's now consider a map F from our manifold into R, okay? Say this is smooth, okay? Because we know what smoothness means. Now, what I can do is I can suppose that I have a curve. Suppose I have a smooth curve gamma, okay, from negative epsilon to epsilon, um, into my manifold, okay. Then F composed with gamma is a curve from negative epsilon to epsilon into R. So it's a curve on R, okay. Does that make sense? So we took some function defined on our manifold that's smooth, and then we took a curve on our manifold, and now we're looking at the composition of these two things, okay. This is called the push forward. So this is there's a push forward pull back. I don't know. The common notation is this. So it's the pullback. This is the pullback of f by gamma. Okay. So this is a curve on R. And now we can ask, okay, what is the derivative of this? So we can look at d by dt at t equals 0 of f of gamma. Right? This makes perfect sense. Okay. And what I'll do is if we think back to multivariable calculus, this is precisely the directional derivative. Okay? This is precisely um, the directional derivative of f in the direction gamma, right? If I remove that time evaluation thing. So at each point t, this is basically the directional derivative of f at gamma. Okay. So this makes total sense. We can talk about derivatives in this case because this map is a function, is a curve on R. Okay. Now, what this means is that we can define tangent vectors as functions. So we can now we can define tangent vectors as functions, tangent vectors at P and M as functions, uh, as functions VP. Okay. So as a function VP that taken smooth curves on, smooth functions on M, okay, and give you a real number with the property that it is linear. Okay. Of course, we want linearity because, we're talking about tangent spaces and we want these to be linear spaces. So if we would want to look at linear maps um, with a property that is linear and VP on a product. Now, if we look back at the product of derivatives, we require it to be to follow chain rule, sorry, not chain rule, product rule, or in other words, Leibniz rule. So we just require that a Leibniz like rule is also followed here. So you have f at p times vp of g plus g of p vp of f. Okay. So now we can define tangent vectors at p as function, blah, 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 blah. Does this make sense? Does why we look at this make sense? Like why we require this arbitrary constraint? Well, it's not quite arbitrary because if we look at the definition of the derivative, you would require it to be um, to follow product rule. So are there any questions on what a tangent vector is? So tangent vectors, just to reiterate, are linear functions on the space of smooth functions. So this huge infinite dimensional space, we're saying tangent vectors at a point P. Um, yeah, so we're saying that tangent vectors at a point P are not actually arrows in space like they were in Rn, but rather they're linear functions on this infinite dimensional linear space that also satisfy product rule. Okay. Now, there's no reason for you to believe that this thing is actually finite dimensional, right? So, no reason to believe this is finite dimensional. Right? Like, because you're taking a huge vector space and then you're taking linear functions on this huge vector space. Um, but you're constraining them a little bit more. And what actually happens is it turns out that these are now actually finite dimensional. Okay. These are finite dimensional. Remarkably, these are indeed finite dimensional. Okay, so let me try to convince you of this. Let me try to convince you of this fact. Um, so the way try to convince you is one, I'll look at tangent vectors in Rn. Okay, in the only things that satisfy this condition in Rn are the partial derivatives and linear combinations of partial derivatives, right? Um, I'm not going to prove that, but if you want, you can look at I know like Eckhard Mind Rankin has a good book on differential geometry. Eckhart's also at U of T, so that's one thing. That's one resource. You could also look into Lee. Lee is the more standard differential geometry, like intro diff geo, like resource. They prove a remarkable fact that this is in fact finite dimensional. But what I'll try to convince you is that only so in Rn, only linear combinations alpha 1 partial 1 at P plus alpha 2 partial. Actually, we've talked about summation convention, right? Um, okay, let me not worry about that too much. So I equals 1 to n partial I partial partial xi at P are tangent vectors. Okay? So it's very important that tangent vectors at P. It's very important that we look at this evaluation at P because if you look at the definition very closely, it uses P. Okay, P is explicitly mentioned in the definition. Yep. So so now, okay, this leads us to the usual identification of these tangent vectors with vectors in Rn because what you can do is you can map this to the vector alpha 1 up to alpha n, and now this is a vector in Rn, right? So you have this isomorphism of vector spaces between these abstract tangent spaces, sorry, abstract tangent vectors and these like concrete tangent vectors. Does that make sense?
Okay, so just one question. Because
Mhm.
if we're talking about abstract vector spaces here, and then we're saying that they're isomorphic, sorry, abstract tangent vectors, and they're isomorphic to the concrete tangent vectors, um, what exactly is that supposed to mean, like from a practical standpoint?
I mean, okay, so the isomorphism, um, one thing to note about the isomorphism is that okay, so we haven't really talked about how tangent vectors look like on arbitrary manifolds yet. Like we know that they like we know what they are. Like we know that they're linear maps from this space into this space. We also um sort of have an idea that they should be like they should form a finite dimensional vector space, right? Um but if you recall from linear algebra, the isomorphic, like we know a classification theorem for finite dimensional vector spaces, right? There's one for each dimension up to isomorphism. But this isomorphism is not canonical. You need a choice of basis, right? Um, this is sort of our choice of basis. And we're just saying that in this, like, in the case of Rn specifically, there's a canonical isomorphism. This is canonical in Rn because this is how we've defined Rn. There's no other way we know what Rn is. And we know what these partial derivatives must mean because we've studied multivariable calculus. So in the case of Rn, this isomorphism is canonical, and you can, if you wanted to, look at tangent vectors not as these linear operators, but rather as these vectors. That's what I'm getting at. But the better way to look at tangent vectors, in my opinion, is to look at them as these linear functions or linear functionals, whichever vocabulary you want to use. I'm just saying that this is what we've called tangent vectors up till this point in our math education. And now I'm saying, okay, this works very well in Rn, no doubt. But when we move to abstract manifolds, this definition does not make any sense because there's no canonical choice of coordinates on an arbitrary manifold. If we had a canonical choice of coordinates, we will see in just a minute that if we choose coordinates on our manifold, then tangent vectors on that manifold also look like these operators, and then you can write them in terms of this and stuff like that. Does that answer your question?
Kind of, but that brings up a second question about bases
Hmm.
and how we choose them and how we can guarantee that our bases always work. And then the final question of how do we prove those bases work.
Okay, so um, so if we look at the definition of the directional derivative, right? Um, and we look at the case of like Rn specifically. So if we have a map from I don't know, so Rn into R, right? We can look at the derivative of this map at a point. So we can look at df at P. And now if you recall, this is a linear map from Rn into R, right? Um, Rn into R. Moreover, in the standard basis, this thing in the standard basis has representation partial f, partial x, partial f, partial x, x1, partial x2, so on, right? This is just the usual Jacobian matrix of a function from R into R. Um, and what this is saying now is in this basis, um, excuse me, in the standard basis, which is the canonical choice of basis for Rn, our derivative looks like this. Now, if you see, this is exactly the basis that I've used here, right? Another thing to note is that the directional derivative of f along like v is defined. I guess some people write it like this, right? Is defined to be df at p evaluated at v, which looks very similar to the definition we have up here. Okay. Um, in case of and now you're saying, okay, how do we choose bases? In Rn, have I convinced you that this is the canonical choice of basis?
Yes, in Rn that's not a problem. It's just when I choose an R, you lose me.
Choose where, sorry?
When I choose an N, right? Sorry, I'm walking, but when I choose an N, right? When I choose, like, say for example, I choose in R56, for example.
Mhm. My Wi-Fi died. Sorry, you completely cut out. My Wi-Fi died, unfortunately. Sorry. Could you repeat that?
Can you hear me? Can you hear
Yep.
me? Testing.
Yes, yes.
Okay. So now, okay. Yes, this makes sense that whenever I choose a canonical, that whenever I have like some n, for example, this works in Rn. But now if I choose, like for example, if I choose like the quaternions, this isn't exactly going to hold there. And then second of all, if I choose like a specific n value to say that, oh, like what if I'm in R to the 56? this also doesn't necessarily hold there.
Okay, so when you're choosing the quaternions, right? There's many ways to look at what the quaternions are. So one way to look at the quaternions is, well, they're the quaternions, right? They're the you can think of them as the span, the R span of the like group, like the the quaternion group of order 8. Okay, so yeah. The quaternion group of order 8, that's one way to look at them. So you can look at them as a group, right? Another way to look at them is they're four copies of R. Another way to look at them is two copies of C, and so on and so on and so on. Right? There are many, many such ways of representing the same space, right? So in that sense, like what you said about the thing that it doesn't hold in the quaternions, that's not true, right? It still holds in the quaternions, right? Because you have a standard basis in the quaternions, which is given by 1, I, j, and k. So you can still define the directional derivative in those directions, right? You can still define that. So that's all I mean by this. This is the directional derivative in that direction. Um, and then when you choose like it just comes out okay. So when you choose like a arbitrary n and you fix that value of n and you ask me, okay, what is the basis of this? Me calling it x, y, z, a, b, c is the same thing as if I said x1, x2, x3, x4, x5, x6, right? Like just because I named them something differently, that doesn't mean that they behave differently. And this is one of the biggest issues with looking at things in coordinates is everything depends on your choice of coordinates. Okay. It just so happens that in Rn, there's a standard canonical choice of coordinates, right? Given by 1, 0, 0, blah, 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 0, 0, 1, 0, blah, 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 and so on and so forth, right? This is a canonical choice of bases in Rn because this is how we've defined Rn. We've defined Rn to be these collection of numbers, right? And then we defined a vector space structure on that. Okay, so all you're doing is you're asking, okay, what is the directional derivative of f in in this direction? Then this would be called this. Then this is this, and then so on. Does that answer your question? Don't worry too much about what um because that's also a philosophical question about like what is this basis? It's just that like from your education, that you have a canonical choice of basis on Rn, and we just leave it at that. We do not like go further than that because it just adds more confusion. Okay. Okay. So now that we have this, let's now look at why the tangent space at a point on a manifold should be finite dimensional. So let P be on the manifold and let U phi be a chart. Um, excuse me, be a chart um, at P in M. Okay, wait, I will trace at P. Actually, sorry. I'm a little scattered-brained. Let's now define using this abstract definition of tangent vector. Um, let's now use this to define what the differential of a map is. So let F be a map from M into N. Um, then df at P, okay, is a map from the tangent space at P uh, on M into the tangent space of f of P at N. So if you remember this, the collection of all of these is the tangent space at M. Um, defined as, so the way you do it is let VP be in TPM, then df at P at VP is now a function, is now a is a function on the space of smooth functions on N uh, into R. So we have to define what it does to a function. So let G be a smooth function on N. Um, then define dfp VP at G to be VP of G composed with F. So let's see this definition makes sense. Okay, so F is a map. Uh, yeah, so F is a map from um, so F is a map from M to N. G is a map from N to R, which means that G compose F is a map from M to R, and we can evaluate, we know what it means to evaluate that at this point. Okay, does this definition of derivative make sense? All this is saying is we're taking the directional derivative of G um, along, okay, sorry. If we say that VP is the velocity vector of some curve, so if VP is the velocity vector of some curve gamma, and what I mean by this is that i.e. Vp of f is the same thing as d by dt at t equals 0 of f of gamma. Okay. Then dfpvpg is the directional derivative of g in the direction of um, f gamma. Okay. I knew I would make this mistake, and that's what I was trying to avoid. So it's f composed with gamma, which is gamma pullback. Okay, so does it make sense as to why this object over here is the directional derivative of um, g in the direction of this in this direction? Does that make sense? Okay. Um, okay, so now we've defined the differential of a map. Um, and I hope that this definition makes sense. Um, so now let's look at something interesting, right? So um, suppose that okay, so an exercise. So actually not an exercise. So now the usual um, the usual theorems of calculus apply. So what I mean by this is if F is a map from M into N and G is a map from N into S is smooth, then we checked that then we checked that G composed with F from M into S is smooth, and that d of g composed with f at p is nothing but dg at f of p composed with df at p. So the chain rule holds. Hence, chain rule holds. Moreover, by the inverse function theorem, if f from n to this is has non-zero derivative and and dim m equals dim n, then f is locally invertible and f inverse um, is differentiable whenever defined. Okay. What this now tells you is hence, so this tells you that if f is a local diffeomorphism, a local diffeomorphism just means that it might not be a diffeomorphism on the entire space, but at each point, there's a neighborhood of that point where f is a diffeomorphism, is a local diffeomorphism, then df at p from TPM into TF of Pn is an isomorphism. Okay? So it's an isomorphism. But this is great news for us because if you recall, so recall that for a chart U phi, we have U is diffeomorphic to phi of U. Right? This is just the definition of what it means for this to be a chart. It's diffeomorphic to this. Hence, TPU is the same thing as T phi of P phi of U. And now note that the inclusion map, right? The inclusion map is a local diffeomorphism in this case, right? It's a local diffeomorphism because at each point on the domain, at each point, this is just identity, and identity is is a trivial diffeomorphism. So what this says is that this thing is isomorphic to just Rm, and this thing is isomorphic to the tangent space at M. But wait, this tells me, hence, that TPM is isomorphic to T phi of P Rm. Hence, and remember we saw that this is just isomorphic to Rm. Hence, TPM is finite dimensional. Okay. Does this make sense? We also have a basis for TPM given by d phi inverse at 5p of partial xi. And this makes sense because d phi at phi d phi at p is a map from TPM into t 5p Rn, which then means that d phi inverse at P using the inverse function theorem is from, so there should be M into TPM. And we know that this is nothing but the span of, like, we have this basis. And so all we're doing is we're pushing this basis forward to get a basis for TPM. Does that make sense? Okay, so given a choice of coordinates on the vector, oh, sorry, on the manifold, we see that um, there's a very nice choice of um, basis on the tangent space of that manifold. Okay, so now let's let's see what um, now using bases and stuff. Let's try to look at what um, let's now look at what the map DF looks like. You know, so let F be a smooth map from M to N. We want to see how DFP um, DFP looks like in this basis. By this basis, I mean D phi inverse 5p partial xi and d psi inverse psi of f of p partial yi. But by chain rule, but it suffices by chain rule and stuff. It suffices to look at maps f from Rn into R, well, I guess Rm into Rn. Um, so I mean we already know what this looks like, but let's just do it anyway. So let G be a smooth function on Rn, then df at P of um, partial xi is not at G is nothing but partial xi evaluated P of G composed with F. But this by chain rule is nothing but sorry, partial G partial yj at f of P times partial fj partial xi at P. Hence, df of P is just the Jacobian. Okay, it's just the Jacobian, it's the usual Jacobian matrix that we've seen. You can now use this to define, look at the coordinate representations of the various vector fields, sorry, of the various tangent vectors that we've seen in physics, such as partial r, partial theta. All of that is outlined in the meeting notes, so you can check that out. Okay, with this out of the way, we've talked about we've defined one of the most important concepts in all of differential geometry. Um, and that's the notion of the derivative and the notion of a tangent vector. Let's now specialize this a little bit and let's try to compute. Let's see what a computation would look like. So for this, I'll introduce a new object called a Lie group. And Lie groups will be central to our study. As we saw that they encode symmetry information, and knowing how all of that plays would be very important. So let G be a group, um, and also be a smooth manifold. So we've seen many such objects. So if we take Rn with addition, we see that it's a group, but it's also a smooth manifold. And these things don't necessarily have anything to do with each other. But what we're going to do is we want them to interact somehow. So we're going to, we then suppose that the maps, so I'll call it mu, from G cross G into G, and iota from G into G, given by GH goes to GH and G goes to G inverse, be smooth. So now there's one question you might ask, okay, what is the smooth structure on G cross G? I leave that as an exercise. Um, there's only one smooth structure that makes any sense, um, to be honest. Like, but yeah. Okay. With this, let's try to compute the differential of these two maps, because with any Lie group, um, these two maps are like the canonical maps that are given with the Lie group. So what is d mu? Let's just do it at the identity, and d iota e. Okay. So to do this, we're gonna try to find a curve. So we want to compute d mu e x e y e on some function f where x e y e come from the tangent space. Okay, so another thing you have to check is that the tangent space of the product is just the product of the tangent spaces. If you want, it's the direct sum of the two tangent spaces. Um, but note that this map is linear, right? Since it's linear, what we're going to do is let um, xe be in the tangent space and let gamma be a curve into G such that gamma of 0 is the identity and gamma prime of 0 will be a little sloppy here, is xe. So remember what this means is that um, uh, this the action like xe. I'll write it once just so that this makes sense. So xe on f is the same thing as d by dt at t equals 0 of f composed with gamma at t. Then let sigma be the curve into G cross G, um, given by
I think you're muted.
Oh, okay. So let me. Since when have I been muted?
Um, that's a good question. You've been writing and you're I didn't see your mouth moving, so I don't know.
I see. Okay, that's an issue. Yeah, sorry about that. Okay, so okay, I've been muted. I don't know. I hope n nothing that I. Oh God. Okay, I don't know. Okay, so what I was saying is we can now compute the derivative of the inverse. Okay, so now, sorry, now we compute d iota e. And we do the exact same thing, okay? But now we need to be a little more clever because we can somehow make use of the multiplication map. Um, right? So note that if I look at the map mu composed with identity on M times the inversion map, and I evaluate this on some group element G, this is nothing but mu of G inverse. But this is just G inverse, which is identity. Okay, so this function is constant. This is constant. And now one must check that the differential of a constant function is zero. Okay, and which again is not too hard if you know how to do it in this multivariable calculus. You know how to do it here because you know that the matrix representation of the map is just the Jacobian. So it has zero derivatives everywhere. So what this tells you is that the derivative of mu composed with identity on M times iota um, at the identity is just zero because it's a constant function everywhere. But now we can use chain rule. We can use chain rule to see that this is d mu at e inverse of xe um, with xe uh sorry um with so it's xe with d iota e xe because you have to compose the differential. But this also equals zero. Um, And we know from the previous part that this is nothing but xe plus d iota e xe 0, which tells you that the derivative or the differential of the inverse map at the identity is nothing but negative itself, which makes sense, right? Because the derivative, so the inverse operation in the standard Lie group, which is Rn with addition, is subtraction, or well, it's negation. But the derivative of negation is like the negative identity map. So this, so we see that that's just a special case of this very beautiful theorem. Okay. Now, why do I look at this? Okay. Why do I look at this? It's because of because if you recall, we gave a lot of importance to the conjugation map. So we placed importance on the conjugation map, right? So it takes in an element H and then gives you G inverse. And note that um, CG at E is E. Why? Because this is G inverse, and this is just G inverse, which is E. Hence, we can differentiate this and get a map. We can get a map from the tangent space at G into the tangent space at G at both at identity. Okay. Um, this tangent space is going to be of utmost importance in our study. So I'll write this as G. Let me not do that. Um, so usually this is written with like a script G. I'm not sure how to write that, so I'm going to write it like this. Okay. Uh, and this is called the Lie algebra. Um, so TEG is called the Lie algebra of G. Um, and so Lie algebras require one additional, so note Lie algebras. If you recall, Lie algebras need a Lie bracket, um, which we will define now. So we need a Lie bracket, and this is why we look at the conjugation map because so we've seen okay, so we have the conjugation map. We take its differential. This gives us um this gives us now a map G. Okay. It takes G and gives you the differential of conjugation at E. Okay. But this is an invertible linear map on a vector space, right? This is an invertible linear map on the vector. And but so this means that we have a map from G into the general linear group um, of G. Hence, we have a representation of G on G. Oh my God. I don't know how to write this properly on G, whatever. Yeah. So this representation is called the adjoint representation. So this is called the adjoint representation. And it's denoted by big AD. So it's AD at G is just the differential of CG at identity. Okay, but why stop here? Let's take the differential of this map. Okay. Um, but before that, let's look at the adjoint representation at the end. Okay, so I sort of jumped the gun here. You can check very simply using the chain rule um, that this should give you a this should give you a representation. So the adjoint representation at identity is nothing but um, DCE at E, but this is just the identity map, as we expect. Um, and and so what this means is that if we take the differential of this map, we get a map from G into excuse me. If we take the differential of this map, we now get a map from the Lie algebra of G into the general linear group of the Lie algebra, given by you take an element X and then you map it over to the differential of the adjoint representation at identity, and then you apply x. Okay. So let's see this definition makes sense. We know that so this vector space over here, sorry, not vector space. Um this Lie group over here is the same Lie group as the general linear group um in Rn, where n is the dimension of the manifold. Um, and so you can like not canonically, but you can say that these two vector spaces are basically the same. Um, Now the tangent space of this would be the same thing as the tangent space of Rn squared, since the general linear group is open, is an open subset of the space of all linear maps. Since it is open, um, and we had the chart where we used the chart to define a local isomorphism to be the inclusion. Using the inclusion, we see that the tangent space at identity of the general linear group is the same thing as the space of all linear maps from V to itself. But since we're working with local diffeomorphisms, at each point um, you will get that this map will be invertible. The differential will be invertible. So you can restrict yourself to the general linear group. Does that make sense?
Yeah.
Okay. Okay. So so now this means that we have a representation. Oh, sorry, I haven't fully explained like why this makes sense, right? So it's okay. The adjoint representation gives you something in the general linear group. Um, and now this thing is a tangent vector. This thing is a tangent vector. Um, well, this thing is in the general linear group, and hence can act on a vector in the Lie algebra, right? So you can define this map small ad of x and y, okay? And what it does is, okay, it takes d, it takes the differential, and then you put x in the first spot, and then you put y in the second spot. Okay, this thing is called the coadjoint representation. I know, very actually let me make sure that this is actually the definition of the coadjoint representation. Yeah, no, this is not the definition of the coadjoint. I knew I was calling it the wrong thing. Um okay, so I guess this is called the adjoint representation of the Lie group. So this thing over here is the adjoint representation of the Lie group. This thing over here is the adjoint representation of the Lie algebra. Um Okay. Does this definition of the adjoint representation of the Lie algebra make sense?
Yes, I think so.
Yeah, so you're essentially just taking the second derivative um of the conjugation map, sort of. Um so if you remember, we briefly talked about how higher order derivatives can be looked at as maps, like can be looked at as things in the tensor product. And so what this says is that AD, okay, from G into G, sorry, cro- G cross G into G, okay, is bilinear, okay, is bilinear. Um, Moreover, one can check that it satisfies um, the conditions for a Lie bracket. Yeah. So in other words, the Lie, the tangent space at identity has a canonical Lie bracket. Okay, has a canonical Lie bracket given by the adjoint representation of its Lie algebra. Um, and this will play a very important role when we um, eventually talk about the eventually when we talk about Lie groups in more generality. So everything I've mentioned, I will reiterate on later on as well. But this is just something that I wanted to just make you aware of. Um, yeah, so are there any questions? Sorry, are there any questions on this? Because I know this is a little, hard to digest, probably, especially if it's new, because it is definitely not something that's easily understood. And I just want to make sure that you understand this because this is a very important concept. Yeah, so does this make sense?
I sent something. Did you see it?
Oh,
Yeah, I was just saying that. Can I like send questions along if like once I've sat on it for a little?
yeah, yeah.
Okay.
Um,
Just for now, it makes sense, but I don't trust that.
okay, so if there are no other questions, I think I will just end it here for now. Um, I will think up some questions and I'll try to outline the proof that this is a Lie bracket on the like sample problems or the problem sheet. But okay, I'll see you then. Bye bye.